welcome back. So what we're looking at today is 5.9 centers of a triangle. So let's go ahead and jump right in. All right, so for this first part, are you ready for a test on Module 5? So basically this is a review of a lot of the stuff that we've done within this lesson because your test is coming up. You will be having your test this week actually. So figure 1 has been rotated 180 degrees about the midpoint inside BC to form figure 2. Figure 1 was then translated to the right to form figure 3. So we moved it there, then we rotate it back, and we went this way. So use figure 3 to explain how you know the exterior angle BCC double prime. So BCC double prime. So this whole angle right here is equal to the sum of the two remote interior angles BAC and ABC. So how can we tell that? Look at what we can see. So we can see from the markings that the angle with the single arc mark, or with the single stripe, angle with the single stripe and the double stripe make the exterior angle. And they are the remote interior angles. So I know that's kind of hard to read, but it says we can see from the markings that the angle with the single stripe and the double stripe make the exterior angle and the remote interior angle. So we can see that. Double stripe here, double stripe, single stripe. These two angles are the same angles that are right here forming this exterior angle that it's asking about. So what you want to do for 2, 3, 4, 5, 6, and 7 is you're going to use these three figures up here at the top, figures 1, 2, and 3, to answer these questions. So using what you can see based on the fact that these are rotations and translations, and that we know under rigid transformations, angle measures and side measures stay the same. They don't change. And it's really going to be working on your understanding of various properties, okay? All right. Writing proofs. So we've got a few proofs here. Prove that line CD is an altitude of triangle ABC. Use the diagram and write a 2-column proof. So first and foremost, circle A is congruent to circle B, and this is given. So that's just, they're congruent. We know that no matter what. That's what I'm giving to you. So that's going to be a part of each of these three proofs, 8, 9, and 10. That should be your first statement in each and every one of them. Part 2. So we're trying to show that CD is the altitude of ABC. So if we look at CE, the full line, CE is a line of reflection. If we folded this in half, it'd be perfect. So CE is supposed to be an E, a line of reflection. 2, reasoning is definition of line of reflection. Spelled it wrong. And our last bit. So then CE is perpendicular bisector, and this is definition of line of reflection. So sometimes we use the exact same reasonings for more than one. And if it's a perpendicular bisector of AB, then it is also the altitude of AB. So in 9, you're going to use a diagram to prove that it's an isosceles triangle. Remember, your first statement and reason is going to be circle A is congruent to circle B and given. It's a three-part proof, just like this last one was. Think about what we know about isosceles. What does that mean? We have to have two sides the same. What do we know about circles and their radiuses and diameters and things? And then in the last one, you're looking to prove that angle A and angle B are congruent. So I want to see you guys be able to work through those. You will have a proof that you'll have to complete on the test. So I want to see that you guys can work through proofs. It's very crucial. All right. Connecting algebra with parallelograms. Use what you know about triangles and parallelograms to find each measure. So here we have line XZ. So line XZ is this full part here. We know that these sides are the same. So as a result, we can take and find, those are 30. The 24, sometimes the numbers on these are a little hard to figure out what they're meaning. This X to the center line, YW, is 24. So if we double that, it would be 48 meters. For measure of angle X, Y, Z, so that's this angle right here. In order to find that, X, Y, Z, it's the whole thing. Whoops. All the way down. So this whole angle is what we're looking for. We know this angle right here is 55, which means that the angle on the other side of it is also going to be 55. So 55 plus 55 is 110 degrees. Now the measure of X, Y, W, so just this smaller portion of the angle, just this part up here above the line, that's going to be 55 degrees, since they have to be the same. Now, YX is this side here. We know all the sides with the tick mark are going to be the same, so it is 30 meters. Now, our next angle, we have YXZ. Okay, yeah, YXZ. Sorry, I was looking at that weird. So just this little angle in here. So we know with parallelograms that consecutive angles add up to 180 degrees. So if this is 110, 180 minus 110 is going to give us 70. And then we know that this is only half of that consecutive angle. So half of 70 is 180 minus 110. 70 divided by 2 is 35. So this angle is 35 degrees. All right, and the last part, we're looking at line YW, so that's this right here. Now, in order to solve for that, we're going to use the Pythagorean theorem, and then we'll have to double our answer. So 30 is our hypotenuse. So 30 squared equals 24 squared plus x squared. So 24 squared is 576. 30 squared is 900. Subtract the 576. So x squared equals 900 minus 576, which is 324. We take the square root of that. And the square root is 18. So x equals 18. So that's just this portion from the center to w, or from the center to y. So then we times that by 2, and we get 36 meters. So same idea for the next section and the next parallelogram. So use what we did in this one, different properties, knowing that consecutive angles are 180 degrees, using the fact that when we have tick marks, we can take and figure out those measures, all of that to take and find these missing values, okay? All right, your keyword for this lesson is proofs. Proofs. If you guys have any questions, feel free to ask.